Welcome to my new episode. In this video we are going to analyze what is digital photogrammetry, in particular what is the difference between digital photogrammetry and analytical photogrammetry. We will talk about some techniques that are used in digital photogrammetry. Let's start with digital photogrammetry. What is the difference between digital and analytical photogrammetry? The difference is that in digital photogrammetry the goal is to analyze an image in a discrete point of view. Indeed, the digital image, is considered as a regular matrix. So let's think about a photo. It can be considered as a matrix, so a set of elements, but instead of numbers here we have pixels, and this pixel give you information about geometry and radiometry. For example, we will see that there are different ways to describe the colors, from a radiometry point of view, but we will see in a while. It is important to understand the resolution. As you can understand, the resolution is due to the pixel. It's really related to the pixel. What is the resolution? The resolution is the capability to distinguish a point in an image. It depends on, as I said, the pixel. How I can measure the resolution in an image? It is possible thanks to the GSD, the ground sample distance, and it is measured as delta multiplied by z divided by the principal distance. To understand this, I have to write a plot. I think it is better to write it in black and then use other colors. So if I'm taking the picture from here and it is my field of view, if my object is here it is my object, or I want, maybe it is, I don't know, here, and I'm taking the picture from this point. Okay, this 8 is Z, so it is Z. This is Z. Then if I want to see what is delta is the pixel size. The pixel size is here, I think you can immediately here there is the pixel. Let's think about here I have the picture. Okay, here there is the object, and here there is like a transformation, and this pixel corresponds to this section in reality. Okay, last but not least, here we have the principal distance, this C. What is the principal distance? This principal distance is the distance between the camera plane and or better, it is better to say it is the distance from the front nodal, or it is better maybe to say the distance between the front nodal point of the lens and the image sensor. In practice, here it's like you have the camera, so it is mostly part of the camera, and with this we can conclude what is the GSD. This is, as I said, really related to the pixel size. It is related to the distance where you are taking the picture, and also it depends on the camera. It is an internal orientation parameter. So let's continue. Now I want to talk about resolution. I want to go in deep with the resolution. There are three kinds of possible resolution. There is the temporal resolution, the radiometric resolution, and the spectral resolution. I start with the radiometric resolution, which is the resolution that is due to the energy that is absorbed by the object. For example, if an object absorbs all the energy and doesn't reflect anything, it is black. So a color which is black is a color that is able to absorb all the energy without reflecting anything. On the other hand, we have Y, that is a color that reflects everything without absorbing anything. In the middle, we have all the set of colors. We can describe with 8 bits a number of colors that is 2 to the power of 8 minus 1, which is 255 possible set of colors. Now let's move to the spectral resolution. The spectral resolution is a way to describe all the colors. There are two main possibilities. One is the panchromatic and one is the multispectra. In multispectra, the most famous I think is RGB, but there are other ways to describe colors. For example, the one that usually printers use, the one with cyan and other colors, I think it is C yellow, and don't remember here. I think I'll put it in the video in post-processing. Then I think I'll continue here. Then in RGB, of course, RGB stands for red, green, and blue. In panchromatic, there is only one band, because here there are 3 bands. Here, if I'm not wrong, there are 4 bands to describe the color. In panchromatic, there is only one band, and they are pretty used in satellite photogrammetry. They are spreadly used in photogrammetry, in satellite photogrammetry, because you have a better resolution. It is due to the energy that is used in the description of the colors. But whatever, we'll talk in another video about this. I was saying there is one band, and the one band for sure is monochromatic, in particular is grayscale. Here there are 3 bands. The 3 bands are due to the band that are visible from our eyes. So we goes from this range, from this wavelength. Maybe it is better to write lambda here. Here. So from 0.4 micron to 0.7 micron, and here you have all the scale from blue to green, arriving to red. And that's it. Now I think it is better to talk about temporal resolution. Temporal resolution is spreadly used in surveying. For example, if you want to understand, if you want to monitor a glacier, what do you have to do? You have simply, okay, maybe it is not really simple, but in general you have to analyze the glacier. You can use satellite photogrammetry, you can use drone photogrammetry. What is important is that you survey the glacier in a specific interval, for example, each 5 years, every year, and so on. And this interval is the temporal resolution, so the time that you use to monitor something. It is important now to talk about the formats, because you can save the image, but you can save the image in many ways, as you can easily understand. Today they are spreadly used the formats JPEG, for example. Maybe it is really it is easy that you know the JPEG format, or PNG, or other formats. In general, formats can be divided in 2 ways. There are lossless, so okay, here I can delete the JPEG. There are lossless formats and lossy formats. Now we will discuss which are these methods. What is important to underline is that a photo in general occupies a lot of space in memory. They keep the original radiometry of the image and a lot of information about the image, but we have to understand how we can manage the weight of the image. In general, when we save an image, when we take up an image, it is important to save it in a lossless format. For example, Tiff. It is pretty used in I can say in era photogrammetry, or in when you perform a DTM, or in other case, for example, in satellite photogrammetry. So in general, in photogrammetry, it is pretty used, but also another kind of method, another kind of format is the BMP. For example, if you want to print the facade of a building, it is better to work with a BMP, because in this way you have the full format and you have all the detail of the rectified image of the facade. But if you want to move the image, maybe, I don't know, if you want to paste the image in a document, or maybe you want also you want to send the image to a friend or something like that, you use JPEG format, as we said. It is a compressed way of spread information. The problem is that if you compress data, you lose details. For example, if here the shape is this one, maybe here it is something like that. Maybe you see here, or maybe. So the problem is that if here you have, okay, here there are 2 pixels. Okay, let's use 3 pixels, that's better. And you have something like that. Maybe this. Maybe here, okay, let's consider, so 3 pixel by 3 pixel. Here you have only 1 pixel and you see only 1 point in a pixel. Or maybe a pixel that is or colored, I don't know. What is important to understand is that here you have more detail than here. But this format reduces the weight of the image about more or less 10 times or something like that. It depends on the kind of compression, it depends on the image details and so on. But now you can understand that it is important to work with image enhancement. With this image enhancement, there are a series of techniques that improve the photo, for example the contrast, in some way to better recognize object. An example is the histogram. If you want to increase the contrast of an image, you have to perform in an image editor the contrast stretching, that is an histogram, and put, for example, the as angle more than 45 degrees. It is only an example. Let's talk about all the possible image enhancement technique. I think that an important method is the moving filters, where you take the picture and you move around the picture, performing a sorting of convolution. It is, I said, a sort of convolution, because convolution is defined in a continuous space, and in image, as I said at the beginning, we work with discrete function, with discrete in general stuff, and so the convolution becomes discrete. So how can describe the convolution from a discrete point of view? I have to work as AEJ, maybe it is better to put a hat here, equal to sum. The sum substitutes the integral of the continuous convolution, where k goes from -1 to 1, and I can use here another this, for example, h minus 1. Here goes from case goes from 1 to 1. I was thinking that maybe it is better, because here we are working on ij, so here I have to be coherent and I have to write I and j. I was thinking about using always 1, and here is because I was thinking to work starting from the first point. I was saying, yeah, so here I have to write that the element of the matrix, or the image, because the image, as we said, is a matrix, is a I plus k and j plus h multiplied by a function, and this function is the filter, and the filter in elements kh. As we said, it is a discrete convolution, and it is computed also in the boundaries. What are these filters? So now we conclude the video talking about this kind of filters. There are two different kind of filters. There are the low frequencies filters that are also called low pass filters, and there are the high pass filter or high frequency masking, filters. So I will write HF. So there are this one. I can talk about some example. For example, in a low frequency filters, there are the neighbor averaging, where each pixel in the image is replaced by the average of the pixel of the matrix. Let's consider a square matrix, for example, n by n matrix, so a squared image. Each pixel in the image is replaced by the average of the pixel centered in xy. Of course, I consider a square image, but only for simplicity. We can work also with the rectangular image, of course. What's important is that this small square, of course, are squared. So let's think about this are full of pixel, for example, 3 by 3. You substitute, instead of each pixel, the average that is present in this box. Another possibility is to use the binomial filtering, where you put more emphasis in the center. For example, here you consider this with a weight. For example, if it is 3 by 3, my square, I multiply this matrix by 1, 1, 1, 1, 3, 1, 1, 1, 1. If it is 5 by 5, I can multiply it by 1, 1, 1, 1, 1. Okay, maybe it is better to increase this dimension. So this, here I write 3, 3, 3, 3, 3, 3, 3. Here always 1, 3, and here 5, and so on. Biggest is the matrix, but the shape will be always this. With 7 by 7, I will have 3, 5, and then 7 or 9, and so on. Or I can write with a different shape. For example, it is only focusing on the center. I can also write 2, 2, 2, and 2, and so here it will change. Or here I can increase the weight. For example, here I can consider 9. In general, this is a binomial filtering. I can also work with a Gaussian filter. So here let's think about a Gaussian in 3D. So maybe this is pretty difficult to write a Gaussian in 3D, but yeah, let's try. So the values in the middle will have biggest weight, and it will decrease going in the boundaries. Of course, the Gaussian is, as we know, continuous. We have to be careful describing a discrete form in a continuous way. Last but not least is the so it was the Gaussian blurring. Another possibility is to use the outlier detection. So for example, if you have an image that is full of noise, not full out, but yeah, if you notice noise in the image, usually it is called salt and pepper image. So like, I don't know, an image, let's think about this image, but with some dots in the image. They are of course outliers. Instead of computing the mean, because the mean, when you have outlier, it is a mess to work with the mean, you have to work with the median, and so you remove the outliers thanks to the median. So if you measure a pixel which is really bigger than the median, it is recognized as an outlier and is removed. These are our low frequency filters. The high frequency filters are, for example, our sharp masking, the variance-based enhancement, and the derivative filters. I want to stop for a while, talk about why we have to use the low or high frequency. Low frequency, if we find outliers, or in general, if we want to increase the quality of the image, and we know that there are some outliers in the image, it is better to use the low frequency to increase the quality of the image, decreasing the quality of the outliers. With high frequency, we want to increase the quality of details. For example, if we want to, for example, let's think about a portrait. I don't know. Okay, it's better maybe if I don't draw anything. But in general, if you want to increase the boundaries of a person that is described in the image, we have to use an high frequency. Some techniques are, for example, the unsharp masking, where you subtract the blurred image from the original to get an unsharp image. So you have like an image where you substitute the image blurred. It is like the image with low frequency filter, and in this way you have an image which is where you see better the boundaries. Let's maybe do it in this way. Okay, you see better the boundaries in the image. Another way to achieve this purpose is to use the variance-based enhancement, where you increase or decrease the contrast by adjusting the local intensity variance. If you increase the pixel difference, it is because the variance is low. So if two elements have a really low variance, you try to increase the pixel difference to see better the let's say the boundary of the image. It adjusts, of course, the local differences of the variance. Oh, sorry, of the local differences in the image. Let's move now on the derivative filters that are the most important between they are the most important among these techniques. You can use the of course the simplest one, so the technique where you use the discrete first derivative with a plus 1 j minus aj divided by delta, where delta is the interval where you are evaluating the derivative. But this method is also the one with I and I minus 1, but also j plus 1 and j minus 1. Sorry, a j and j minus 1, or j plus 1 and j. They are not really used because they are not really efficient. It is better to use the derivative evaluated in okay, let's describe it in this way. So I plus 1 j minus I minus 1 I minus 1 j, okay, evaluating, sorry, on to delta, because we consider the point after and before the point where we are evaluating the derivative. Delta, as we said, is the dimension of the single pixel, and we compute the derivative in two directions, of course, in I and in j. So j plus 1 minus j minus 1, as always, on to delta, and we build the matrix. The matrix will be, as you can imagine, for rows it will be 1 2 minus 1, sorry, it is 1 0 minus 1 0 minus 2 0 minus 1. Okay, and for columns, if you are derivating by columns, it will be 1 2 1 0 0 0 minus 1 minus 2 minus 1. It can be easily derived by the form of the derivative. Okay, if we need the Laplacian to see the borders, as we did before, if you want to strongly see the borders, we have not to consider the first derivative, where we see how the color changes, but it is important to see how much it changes. So the derivative of the derivative, so the second derivative, and so we have to consider the Laplacian, and the matrix becomes this way: 1, all 1, and in the middle you have 8. In this way you consider the Laplacian. With this I can conclude the video about digital photogrammetry.